Hello and welcome to my ENEL383 project demonstration video. In this project, we had to create a dual tone detector that drives a green LED when 1.54 kHz is applied and switches to drive a red LED when 2.3 kHz is applied. This system will also operate from a single 9-volt battery to get full marks. So how did I go about doing this? So first, I designed some various filters here to see what kinds of output voltages I would be getting at the two different frequencies that I would be detecting. So that resulted in this table here. So as you see, we have the 4 different filters: 1.54 kHz low pass, 1.54 kHz high pass, 2.3 kHz low pass, and 2.3 kHz high pass. So after thinking about some theory of operation and how to get this to work, I picked the 1.5 kHz high pass and the 2.3 kHz low pass. And what can be observed here is that when 1.54 kHz is applied to these two, we can see that the output of the high pass filter is lower than the output of the low pass filter, and then vice versa when 2.3 kHz is applied. So then we can utilize a difference amplifier to detect when that situation happens. So first, the signal goes into an input buffer, so that way these two filters do not see each other at all. Then that goes into some sort of ×4 gain op amp of some kind. Then that signal is rectified, and then that gets fed into the difference amplifier. So when 1.54 kHz is applied, V2 minus V1, that is a positive difference. So when the difference amplifier outputs a positive, that means the inverting Schmitt will go negative and drive our green LED. And vice versa, when 2.3 kHz is applied, V2 minus V1 is negative, and therefore the inverting Schmitt will output positive and turn on the red LED to indicate 2.3 kHz. So that is a theory of operation from this block diagram. And then let's walk through my schematic here. So as you can see here, we got our two input buffers, our two input buffer amplifiers here, and then just some unity gain. They're just some unity gain non-inverting op amps. Then up here you have our 1.54 kHz high pass filter and 2.3 kHz low pass filter. So these two op amps here, they will be ADTL 082. These four here will be an OP482. Then these two, you can see here, there are some these are the ×4 amplifiers here. Now as you can observe here too, this amplifier is inverting and this one's a non-inverting. The reason for that is because the two filters because this is a high pass and this is a low pass. That means the signals coming out of here will be approximately 180 degrees out of phase from each other. So then having these two different styles of amplifiers here will hopefully correct that 180 degrees phase shift so that the peaks are lined up with each other. Then you got some 1N419s here to rectify the signal, so you just get rid of all the negative peaks. And that is fed into a 2x difference amplifier here. And then that goes into our Schmitt trigger. And these two op amps are an OP484. The reason for 484 is because it's rail to rail, and that makes setting the output of the or the threshold of the Schmitt just a little bit easier. Now, as you can see here, I have some 1 microfarad capacitors here. The reason for that is because, as I said earlier, the phase difference between these two filters here is approximately 180 degrees, but it's not exactly 180 degrees. Because the peaks are just coming out of this section here are just a little bit off from each other. That means when we do math on it with the difference amplifier, there are some undesired negative and positive spikes when you should only be getting a negative or positive difference. So that is undesirable because that'll mess up our Schmitt. So to correct that, I put some filter capacitors here to get a DC voltage. So that way we don't have to try and deal with those negative and positive spikes, where you should only be getting a negative or positive difference. So yeah, that is my schematic here. So then here is the actual construction. As you see, it looks like an absolute mess. So up here, we got the ADTL082, and that's being used as the input buffers, as I stated earlier. Then you got your OP482 down here, and that is again being used for the two different filters. As you see, this side over here, this side is our 2.3 kilohertz high pass, low pass filter, and then on this side here, we got our you can't really see it too well, but we got our 1.54 kilohertz high pass filter here. And then towards the bottom of the op amp, we got our two different times for amplifiers there, and we got our two diodes you can see there, and there's the capacitors for filtering. Then finally, we got our OP484 sitting down there. As you see, the bottom 2 amps are not being used for anything. Originally, I was going to use an 808542, but I cooked it because I fed a signal into it without any power. Whoops. So then, that was a very good op amp. I would have loved to have an extra rail-to-rail op amp sitting around. Well, dumb me. Then that finally feeds to these two LEDs here with the 1K current limiting resistor. And then for power, we got the LTM8067 here for -5 volts, and the LT3080 with for the positive 5 volts. As you see, here's my very ugly chain of 3 resistors here to set the voltage for it. So then let's test this thing. So I'm just going to put my phone down and hook up the battery because I need 2 hands for this. So as you see, we are on here, and when I connected to the battery, it defaults to the green LED. But for some reason, when I was originally powering it with the Analog Discovery 2 here, it would default to red. Well, let's look here. So let's dial in. We got 1.54 kilohertz there. Let's turn that on and feed the signal. And as you see, our green LED is on, as expected, with 1.54 kilohertz. So then, let's dial in 2.3 kilohertz here. And as you can see, there is our red LED for 2.3 kilohertz. So now let's stop the feeding the signal in, and as you can see, the circuit retains its state. And now let's go back to 1.54 kilohertz here. And click run. And there's our green LED. And then let's stop feeding the signal. And as you see, the circuit retained its state. So as you can see here, the circuit did exactly as expected, and it is powered from a single 9-volt battery here. So, yeah, it works exactly as expected.